I'm far from like an expert in machine learning, but I've learned some stuff, and I wanted to throw all the little tidbits that I've learned at you guys so you can also learn tidbits. So what I want to take you through today is three things. Firstly is just a kind of introduction to machine learning, like what is it, kind of conceptually, what are the problems that it's trying to solve. Then I want to kind of zero in on one specific machine learning technique. I'm going to go for an algorithm called word-to-vec. And the idea is I just want to kind of like maybe demystify machine learning a little bit. I think it's one of those things that a lot of people are like, oh, machine learning, science, and it's not actually all that complicated. And then finally, I'm going to end up on just some thought starters on kind of how we can use machine learning as a tool for ourselves as well. This isn't something that you have to be Google kind of at that sort of scale to use. Like it's very accessible for people to kind of use at the level of problems that we're trying to solve for our clients. So just to kind of like talk through how you might use machine learning, we're going to talk about creating an app called Petter. And the pitch for Petter is it's going to be an app that will use machine learning to decide if you can pet something without that thing turning around and murdering you. And just in case this does go out on the internet as an acknowledgement, some of these slides I've shamelessly stolen from an old colleague of mine, Malcolm Slade at J-Wing. But I'm pretty sure he stole them from someone else, so circle of life. Should you pet this bear? Probably not. Probably not the smartest idea. And that's what our pretend app is going to kind of try and figure out. Now, the first thing you need to do if you wanted to create an app that does that is start coming up with a list, right? So you'd have a database and you'd say, can you pet a bear? No. Can you pet a kitten? Yes. So on and so forth. So you'd have this big list of everything you've got. Should you pet it? Yes or no? Now, computers don't know what a bear is. So you need to teach your computer what a bear is so it can say, is this a bear? Yes or no? And then look it up against this table. So what is a bear? Well, you could start coming up with rules. So if somebody was to ask you to describe a bear, you might say something like, well, a bear has 4 legs. A bear is furry. A bear could be brown. Is this a bear? No. Or if it is, it's a bear that's eaten something very strange. So maybe you start layering on more rules on top of it. So you might say, oh, a bear's got sharp teeth. A bear has 2 eyes. A bear growls. Is this a bear? No, but it matches that description. Now, if you were to sit there and kind of come up with enough rules, eventually on a long enough timeline, you would have an algorithm that could just about recognize a bear. So you've got one line of that table in. Now, after all that expense, if you then pointed your phone at a lion and said, can you hug it? It would go, well, it's not a bear, so yeah, sure, have at it. Now, the principle behind machine learning is to come at kind of this problem from a different angle, and it's using kind of neuroscience, kind of the way that a human or maybe mammal brain works as a way of and trying to replicate that in software to kind of replicate the way that humans make decisions. So if you think about the human brain, when you're a kid, you don't know anything. So you might go marching up to a bear because you've got no idea even what danger is. Like that's not something that's in your head. But eventually over time, you start learning, and what happens in the brain is neurons get created. So these are kind of little points in your brain that are, you might have a neuron for do not pet, will hurt you. And then that will be connected to other things that you've learned to associate with that thing. So you might have a neuron that says this is a bear, and that's connected to do not pet. But that connection for bear would also be connected to big teeth. It might be connected to muscles. It might be connected to eyes facing forward, which means it's a predator. Like the human brain doesn't just say have one neuron for a brain. It has this whole clump of things that you kind of associate with kind of a bear. It's all about kind of creating associations. So if you take the term bear out, and you're looking at a lion, and you've never seen a lion before, you have no idea what it is, but you know a bear has big teeth in his muscles and could kind of cause some damage. You can then use those learnings and kind of look at your lion and say, okay, I probably shouldn't get too close to that. Bad things will happen. This is how we kind of allow knowledge to be transferred. So you could take any animal that kind of has similar characteristics to a bear, and because you've learned that hugging a bear would go badly for you, you can reasonably extrapolate out that hugging kind of these creatures would be bad for you. It's not perfect. If you were to show a 4-year-old a fox, they would probably point at it and go doggy, because 4-year-olds are stupid. But what they're doing is they're sort of looking at it and it's firing enough of those neurons in their brain because it's similar enough to a dog that they're kind of bringing the closest experience they've got to what they're looking at. And this is, even once you kind of know what a fox is and you know kind of the things that distinguish a fox from a dog, there's still enough kind of overlap there that you instinctively know that they're related, and that there's a lot of similarities there. So the way machine learning kind of conceptually works, it's the same way that a human being learns, right? You see lots of dogs, you see lots of foxes, you learn the difference between the two, and then you're able to recognize a dog from a fox normally. Same with machine learning, you kind of load up a lot of training data. So for our app, that might be lots of labeled animal pictures. And you maybe label them not as this is a lion, this is a bear, this is a gull, but you might label them as dangerous, not dangerous. And eventually that will create all the neurons and kind of patterns will start to emerge, and your machine learning algorithm will start to recognize, okay, this new photo is similar enough to things that are marked dangerous. I'm going to make a prediction, and that prediction is you shouldn't hug it, and then vice versa. So that's basically the principle behind all machine learning. What I'm going to do now is delve into one technique just to kind of pull apart how, on a granular level, kind of these techniques work. Machine learning is not one thing. Machine learning is a whole family of different algorithms and different approaches. And the real art of kind of machine learning is about trying different ones, mixing and matching them, figuring out how to make your machine predict something as accurate, give you kind of accurate predictions. Word2Vec, this algorithm, the technical term for it is it's about translating vast chunks of text into vector space in order to figure out coefficients, which sounds big and scientific, but it's actually fairly straightforward when you break down what that means. Say you're creating a search engine, right? Somebody's searching hotels in London, right? And you want to predict what's the best website that I want to put in front of the person who searched hotels in London. Now, I think something like 300,000 people search that every month. So there's or at least in a normal year, probably not now. So that's a pretty big data set, right? And Google can probably do some reasonable predictions based on kind of what those 300,000 people have engaged with. But what would be better for Google is if they can figure out, the more data they can crunch, the more nuance they will find in things that correlate with the result they want, which is a website that people are going to engage with. So it's actually better for Google if they can look at a much larger data set and say, okay, we know London is a large European city. What lessons can we take from all large European cities? Like there's going to be similarities between the user behavior in, say, London and Paris. So Google may want to figure out, okay, what people engage with in Paris, and then extrapolate that out into London. Now, a computer doesn't know what a London is, it doesn't know what a Paris is, it doesn't know what a hotel is. Like, you need a way at scale to kind of teach it these things. Now, in Google's case, that's not actually true because they pay Wikipedia a lot of money to basically create a database of this stuff, but let's pretend they didn't, because that's inconvenient. Let's take two documents. So you've got two completely independent websites, nothing linking them between them, completely different authors, not owned by the same people, two completely different pages, but one is talking about London, one is talking about Paris. Now, how can you figure out that they're both, there's a relationship between those two things just from this completely unstructured text? The way Word2Vec would do this is it would put a graph over the top of it. So if you can imagine you just drew kind of two axes over the top of a document, right, okay, let's dig into London first. So here's two words. London is at 3 rows up, -1, so one word to the left on our graph. And then the word largest is 2 rows up, 1 to the left on our graph. So the distance between those two words is 1. And then if you take our completely different document on the right here, Paris, 3 words up, 1 word to the left. Largest, 2 O's up, 1 to the left. Again, the distance there is 1. So what Word2Vec can do is start figuring out, okay, where are words being commonly associated with each other, and use those to kind of connect them. So what Google can then do is say, okay, somebody searched hotels in London, that's 1 away from largest. Somebody searched hotels in Paris, that's 1 away from largest. Right, okay, there may be 1 strand. If London and Paris are 2 neurons, there's 1 strand now connecting those 2. And with enough strands, Google, our search engine, can start sitting here and going, okay, I understand that there's a lot of similarities between the thing that is London and the thing that is Paris. Right, I'm going to start using all that user data that's historically Paris searches and kind of applying that to figure out what's best in London and vice versa. Now, so that's a very tenuous link if you're just looking at 1 document. If you're Google, you have the entire internet at your disposal. So Google can do this across billions and billions of documents and start working out, okay, where are these kind of word pairings, word relationships coming up again and again and again and again. And then once it hits a critical mass, then you can start weighting and saying how connected is the word London from the word Paris. And you can start saying, okay, those 2 words are much more connected than the word London and the word banana, even though there's nothing actually, you don't have anything structured there that says London equals city, Paris equals city. Like, just from this associated line, you can work out kind of where the similarities are, even though it doesn't know what a city is. And this is what that just looked like visualized. So the more associations you've got, the closer kind of each of those nodes are together, and they kind of start to form clusters. So in a cluster, you might start getting every single European city or every single big city, and you start working out, okay, where are things kind of similar to eeach other. And that's how you can then start taking the signals from everything in that cluster and use that to kind of get more sophisticated learnings than if you were just looking at the 300,000 people who searched hotels in London. This does, I think this is definitely true in SEO, but I think this is increasingly true for any platform. This creates what AI researchers call the black box problem. The maths behind kind of creating 1 of those strands is fairly straightforward, but when you've got a billion of them, it doesn't matter how you visualize that. That's just too much information for a human being to kind of look at and interpret. So in SEO, very often we get questions from clients like, if I build these links, what will happen? Which isn't an unreasonable question. They want to know what they're spending their money on. But the thing is, we don't know how valuable links are in that big soup, because Word2Vec might be 1 input of 50 different similar machine learning techniques that are all then got another layer of machine learning that's interpreting the results. There's no way to kind of know, okay, this is going to be the impact of this 1 thing that goes in. And what it starts to create is a situation where you can do the same thing for 10 websites and it will work brilliantly on 5 of them and will do nothing for the other 5. And we've got no way of knowing and predicting kind of what those 5 are going to be. It's why in SEO we're talking a lot more about kind of doing test and learns and kind of doing things where we roll out minimum viable tests on different pages and then kind of figuring out, okay, what's the impact of this going to be on Google, what the impact of this going to be on users, and then doing that as a first layer before we make big recommendations. Because if you're a client, if we're going to recommend a massive development task, you want to know, they want to know that they're going to get a return on it, right? And kind of stealing a bit of kind of what the CRO and the UX design industry has been doing for decades and applying it to this, I think is the solution to the black box problem. I don't know why that slide's there. Anyway, this is a bit of a tangent, but this sort of is the reason why I think antitrust is going to be probably the biggest story that affects us over the next 2-3 years. Because what this means is whoever has the data, it becomes a moat to their business that nobody can breach. So if you're Google, somebody searches, they get a little bit more information about kind of what that person engages with. They apply that back to their machine learning algorithm. Their machine learning gets that little bit better. Their machine learning therefore can serve better results, which then means that more users are going to use it. It becomes this kind of flywheel where it just grows and grows and grows and grows. One analogy I read was if Google just open sourced their algorithms, which a lot of them they actually have. That's basically what TensorFlow is. If Google open sources their algorithms, and so Google and Bing have got the exact same algorithm. If Google's got 50.1% of the market and Bing's got 49.9% of the market, Google wins because Google will just exponentially get better and better at Bing. Bing will get worse and worse and worse. Google ultimately takes the entire market. And I think in this last year, kind of regulators have started to wake up to the fact that kind of pre-internet kind of antitrust regulation isn't really set up to kind of put checks and balances on companies that work this way. And I think that's going to start having a downstream effect on kind of what ad units are available, kind of what featured snippets are available, how you can target people. I think regulation is going to really be the big story kind of over the next 3-4 years. And then just on a final point, so machine learning, obviously, if you wanted to create your own search engine, you'd need Google level resources. But none of our clients are trying to create their own search engine. So at the sort of scale we work at, these are actually very accessible tools that we can start putting into our own workflows and kind of using to solve our clients' problems. So like I said at the start, training machine learning algorithm, relatively straightforward. You take a big data set, you put it through its training, and typically what you do is you'd split it into 90-10. So you'd have hundreds of or tens of thousands of classified photos. You train it on 90% of it and then use it to do predictions on the other 10 and compare those back to what the right answer should be. And that gives you what's called a confidence score. So you put it through, to use our app for an example, you might put through 100,000 photos, keep 10,000 back, and then what it will do is see how accurate was the predictions on those 10,000 versus reality. And if it says, well, okay, we were 98% accurate, maybe you'd say, okay, great, we've got enough data, let's roll that model out. If it was 5% accurate, then don't. And if you come up with a low confidence score, then you just put more data in, or maybe you adjust the input. So you say, okay, maybe I need to, I know, take color out of the photos, something like that, make the photos black and white, maybe that will improve, kind of remove some of the noise and improve its ability to predict. If we use machine learning, we have to be very careful because it's very easy to accidentally put in biases that none of us would ever want in the algorithm in there. So when I wrote this deck a couple of months ago, this was something that literally the same day I was writing this deck, this happened. This guy tweeted out an experiment where he took this photo on the right, which was a picture of Barack Obama, a picture of Mitch McConnell, kind of with a big white strip in the middle. But this was all one file, this image on the right, and just saw, okay, what would Twitter's algorithm pick as the kind of snapshot to put in the tweet? And it did this. It put the white guy in twice. Then he did a follow-on experiment where he took and inverted the colors and also changed the tone slightly, just to kind of remove race from the equation. And suddenly Twitter's algorithms recognized both people in the photo. Now, I don't think Twitter set out to create a racist algorithm, but what they've done is they've taken a library of a few million photos and just bundled that into the machine learning algorithm without thinking and checking about kind of what biases might be in that data set. And what's ended up happening is it's probably 70% of the photos in there were white guys. So now that algorithm kind of relates kind of skin color as kind of one of its inputs. That's something that this is a fairly kind of overt example, but it's easy to stumble into as well. So for example, if you used postcode as an input, so say you were trying to say, right, okay, I've got an ad, it's doing a discount to people I think I'm going to buy, I want to kind of target that programmatically, and postcode is one of the columns in your training data. Well, certainly, especially in large cities, kind of communities tend to kind of live close to each other. So you've inadvertently created a proxy signal for something like race, nationality, religion, even if that's not something you've explicitly kind of put in your data set. So it's just something we have to be very, very careful of is be aware not just of overt biases in the data, but also where we've kind of got proxy signals for biases that could accidentally sneak in. There's kind of 3 sets of tools you can use for machine learning. A lot of these are open source algorithms. So particularly if you know how to code and actually code to a very basic level. Like as long as you can do a basic loop, you can kind of build and run a lot of this stuff off your own machines. There's cloud services. Where you can kind of package your data up. And a lot of them you don't even need any sort of programming knowledge. A lot of them are completely graphical interface based. So you don't need to write a line of code to be able to utilize them. And there's a lot of just pre-built models out there as well that you can potentially use. I won't go too into the build and run yourself. I think, as I said, step one of that is learn to code. Although I kind of wanted to, because I wanted to see if I could get Rob and Lou to buy us all wicked sick gaming PCs. Cloud services and pre-built models are realistically the ones that we're probably going to look to use. So this was an experiment I ran about 5 years ago, where anyone who's ever done keyword research knows one of the most time-draining parts of it is classifying the keywords. So sitting there and saying, this person searched for hotels in London. That is a search for a hotel. That is a modifier, is the city. They want a hotel in the city. And then at the end of it, you can start graphing out, okay, this is how many people are searching for hotels in a city versus searching hotels by price. Very laborious task, very soul crushing, very good way to drive yourself to drink. And also after a while, your brain just completely turns off. The error rate when you look back at it is very high because you do this for 3 days, your brain is mush. I used AWS's platform, which I can't find anymore. I think they've taken it down. But I classified 5% of my data set, uploaded that, trained it, used it to train a machine learning model, and then gave it the other 95%. And it came out with about 65% of it being right, which doesn't sound hugely impressive, but that's probably better than I would have done if I'd done it by hand. And to be honest, a lot of that probably was reflecting kind of errors I'd done in the 5% as well. I had that, and I had more time, I could have made that 5% input very, very clean, and checked every line, double checked it, triple checked it. That probably could have been substantially higher. So that right off the bat, that's a massive time saving that kind of machine learning could potentially drive. Like I said, I couldn't find the AWS one anymore. I've got a feeling it's either been rebadged or renamed, or AWS is just a nightmare. But Google has one that's very similar called AutoML. And again, you don't need to be a programmer for this. You can just, it's all about uploading CSVs and then clicking the right buttons in the right order to train your model and test against it. And I put this link here if anybody wants to start playing with that. That's a tutorial on how to get started. And then there's pre-built models. So for example, this is Google Image, Google's cloud image platform. You can upload any image to it and it will start tagging it, tell you what the features are. Sometimes it can even, like you can upload a picture of a random, it was one I did a while back, where I uploaded a picture of a random hill and it was able to figure out the latitude and longitude of it and kind of plot it on Google Maps for you. So it can do some really, really sophisticated tagging. And Google's got a whole range of these. It's also got things for kind of text classification, where they've trained the model, they've kind of built everything to make the predictions, and all you have to do is give it what you want it to predict, and it will come back with answers. So this could be very good for something like, I don't know, potentially if you've got something that's very image heavy, like ArtFinder, for example, this could be something that you'd use to do kind of alt text at extreme scale, where it's not practical to spend like kind of enough man hours to tag every single image, and no one image is individually kind of that important. This could do it in bulk, and then you kind of get the uplift from doing kind of a massive amount of that work collectively.